This is an afternoon session on large-scale LLM training in JAX. I am Jacob. I have been a DeepMind for a while. I've worked on Gemini, doing a lot of both training and serving infrastructure, and I'm going to be talking about both a little bit. I think generally this talk is aimed at just convincing you that JAX has sort of done a really good job of serving as like a kind of drop-in solution for really, really large-scale training in a way that PyTorch and like no other framework really has, with some like important asterisks that I think we're going to talk about. I think the thing I want to really try to emphasize is that JAX does a really good job of allowing you to like both write really simple code, essentially write NumPy code, and then just distribute it to potentially tens of thousands or hundreds of thousands of devices without really any changes. And it gives you the tools to control how that distribution happens at a very granular level. And I think generally it does a good job via the XLA compiler of kind of just doing the right thing. If you write NumPy code and then just sort of say run on 100 or 1,000 TPUs or GPUs, it will generally do the right thing. But it also does a pretty good job now at giving you sort of intermediate APIs for taking control back from the compiler and telling it to do something if it's doing something wrong. And so there's this kind of development loop that I think is very important that I'm going to try to emphasize, which is like write some code in NumPy, run it on a bunch of devices, being pretty explicit about what you want, profile it using what I think are some pretty good profiling tools that we have access to, have enough of an understanding of the roofline of what you're doing to know if it's sort of within an order of magnitude of the performance you expect, and then go and focus on the areas that actually aren't performing up to spec and try to fix them. And so I'm going to mostly do a live demo. I want to emphasize some of the really cool new parallelism APIs that you can now use. And I also happy for this to be pretty interactive. So if anyone has questions or comments or just wants to shout things out, that sounds great. This is going to be focused generally on this little horrible little fake transformer I made. It's not really a transformer. It doesn't have a tension. It has one layer, and it won't really do anything good. But I'm going to kind of use it for a little bit as a example of what you can do in JAX. So we're going to train a little model, a little version of this. So I think everyone can probably see this. This is a little notebook I have. Here is our little transformer. And so the first thing you can see is we've just written this essentially in NumPy with JAX, JAX NumPy, JAX dot. And I'm running this right now on a collab that I have connected to a backend with 64 TPUs. So this is already a pretty nice thing that the JAX ecosystem has done a good job of. This is using a system that we've recently kind of made available called Pathways that kind of abstracts away the fact that you have multiple JAX hosts. So historically, if anyone has done this, when you write JAX at a very large scale, you typically write what's called multi-controller JAX, where you write a version of JAX that runs locally on every host, every CPU that has a set of GPUs or TPUs attached to it. And here I'm just able to pretend like I just am on a single controller with a giant set of GPU devices. And in fact, what I can do is I can actually create, if I just jump down here for a second, I can make a little mesh of my devices. So here I am, and I have my 64 devices, and I've now kind of laid them out in a nice linear way. So I have my 64 devices, and I can do stuff with this. I can put data. I can send data to these devices. I can shard them. I can run computation on them. So first thing I'm going to do is just kind of actually run this little transformer. So I just have batch size of 64, some small sequence length, some vocab size, a few of the sort of hidden parameters. And I'm just going to make my parameters. And I'm going to call jax.jit on this function, which is kind of the familiar way of writing JAX. And I'm going to call it. And here I'm going to profile it. And so this is going to be the first moment where we actually write some code, run it, and then profile it. And this is using this xprof profiler, which is available to anyone who wants. It's sometimes called the JAX profiler something. The naming is inconsistent, as usual. And so we can look at this, and we can see that it ran. And we can kind of actually try to break down what's going on here. So there are a bunch of these little things called fusions. And in JAX world or XLA world, a fusion is generally a matrix multiplication, and some other stuff. Typically what, especially on TPUs is done, although it's true in GPUs as well, is you have some parameters stored in HBM, DRAM. You kind of load them out and you send them to the tensor core, or the MXU in the TPU case, does a matrix multiplication, and then you do some extra stuff. Like in this case, for example, this thing here called convolution maximum fusion. I don't know if anyone can guess what that is. That is a fusion of a matmul and a ReLU, because the ReLU is just a max of the output and 0. So it is like streaming these weights out, sending them to the MXU, running a ReLU, which just runs in what's called the VPU on TPU, and then sending them back. And it's kind of interesting to look at this because we can say, for example, how long did this take? It took about 90 milliseconds. Now we can ask ourselves, how long should this have taken? And well, we can actually just look at what this op was. So this is just this, essentially this, like jnumpy dot dot with a ReLU. And if I look at the shape of this, so I am doing a 64, essentially a 64 times 1024 by 8192 times 8192 16384 matmul. This is like the operation I'm doing. If we ask, and this has been discussed previously in the various other sessions, this is essentially doing 2 times 64 times 1024 times 8192 times 16384 flops. And so I now have this large number, which I won't even try to say. But if I actually go and look at, I'm running this on a TPU V5E slice. This is one of our latest sort of inference chips. And if I go and actually look at stats I have for this, I will notice that TPU V5E does about 1.97 E14 bfloat 16 flops per second. So I go do this, and I divide by 1.97 E14, and I get 89.3 milliseconds. And how long did it take? It took 90.932 milliseconds. So pretty good. We can actually divide those numbers. So 89.3 divided by 90.932. We're getting about 98% flops utilization from this, which is pretty good. That is to say, like, our XLA, the MXU, is doing its job. It's actually doing a big matmul reasonably well. And so, we can go and do this for every other op. Like, this is the embedding table fusion, like looking up the tokens, the embeddings in the embedding table. This is that down projection. And this is the output, like, embedding projection. So we have these kind of like 4 big fusions. And then we could even zoom in here. And this is going to be the log softmax. We did it at the end, and you can kind of like, it's actually kind of fun to think like, okay, I can look up how long, like, how many cycles it should take to do a logarithm in the TPU. And, you could run the same thing on a GPU, and you kind of could like do some math about CUDA cores, and like, you learn something. And so, kind of like, I've now gone and said, okay, this actually seems to be doing pretty well. But notably, when we were doing this roofline, we are just looking at a single TPU. Like, the number I looked up was the flops for a single TPU. And so, well, I said we were running on a device, like a set of 64 devices. So what's going on? Well, I didn't really specify anything. So by default, it just ran on TPU 0, which is kind of whatever. It's fine. But I can now go and say, I'm going to skip that for a second. I'm going to say, OK, I'm going to make this mesh that we talked about before. So I've now sort of told it how I want to think about my devices. I'm going to pretend like they're all just in this single linear chain. They're not actually. TPUs tend to be, especially here, they're in these 2D toroidal structures. So they're all they're in this like 2D grid, and they're all connected to each other. But I'm kind of just going to pretend like they're all in a line. And XLA will figure out how to do anything I ask it to pretty efficiently. And so now I'm going to do this sort of magic thing. I'm going to just device put tokens to, essentially, I'm going to say tokens has 2 axes, the batch and the sequence axis. I'm going to say shard the batch axis over the data dimension, which I said before was, kind of mapped onto this linear set of 64 TPUs. So I've laid them out. I've said this axis is called data. Now I'm going to say I want my tokens to be sharded along the batch spread. And what is this? Well, it's data parallelism. I'm just saying I want my batch to be split up. And now what am I going to do? Well, first of all, I can look at my tokens. They're fake tokens. They don't actually have anything in them. But I can look at how they're sharded. And so you can see this is the 1024 axis, and this is the 64 axis. And I can see that by this nice color scheme, like every, each TPU essentially has one sequence of length 1024 locally. And so what do I do now? Well, I can just run the same function. I'm running exactly the same forward path I did before. But But now the input is sharded. And the weights of themselves are unsharded. I didn't specify anything. And now I can look at this trace, and we can kind of do the same thing. And well, okay, we'll zoom in here eventually. And you can see this looks very similar. Like these kind of look the same. You see the same operations, except how long did this take? It took 1.4 milliseconds. So it took, how long before? Like 90 milliseconds. So we got like a big speed up from using, way more GPUs, which is good. We kind of expect that. And of course, this is an interesting case because there isn't actually any communication needed. Like we're just doing trivial, like sort of embarrassingly parallel work across these. But in real LLMs, really in anything, like there is some communication that needs to happen. So something that I had just thrown in here is like the simplest possible training step. So here we took the forward function, and then we essentially used it to compute logits, and then we sort of took the target logits. Like this is how you would train a LLM. So you got the log probs, you took the next token log probs for some set of targets, you take the negative log likelihood. This is like the standard sort of cross entropy objective for an LLM. Now you compute jax.grad, which is like this magic thing that JAX does where it computes the gradient of any function you give it. And now I'm telling it to compute the gradient with respect to the embedding, the weights, et cetera. And then I've passed in, that was a typo, but I passed in the learning rate, and I'm just going to take a gradient step. So this is like the very simplest possible gradient descent training step. And I'm, again, I'm faking everything. So I'm just going to pretend we have some tokens, and the targets are the next tokens. They're all zeros, so it doesn't matter. But the point is, first of all, I can run this, and this all just works. But in particular, now I could go to where I had profiled this before, and you failed. I live coded this with some difficulty in the last session, but I'm just going to run this, the same deal. And specifically here, now X and Y are sharded in the same way that they are, they were before. Now I can look at this profile, and you can see it actually looks quite different. You still see, there are some fusions here doing stuff. But now there is this giant all reduce here. So it has now gone and it has realized that because we are computing a forward pass, we are computing a loss, then we are averaging that loss and then sort of computing the derivatives backwards. What it's done is it's saying, okay, well, we can actually even look at what it's all reducing here. It's all reducing, this is the output matrix. So I don't know how small any of these things are, but this is the output matrix. So we've computed the derivative with respect to this matrix, and then this is like the derivative of that of the loss with respect to that matrix. We are all reducing it, which takes some amount of time, and then we are continuing the backward pass and doing another all reduce. This is the most standard form of data parallelism. But the point is, XLA has decided how to do this. It has decided that it needs this all reduce. We didn't tell it. It just realized that there was this mean across the batch. And if we went back and removed the sharding on the tokens, this would go away. And we can do some nice things here. One is we can ask how long did this take. So there's an all reduce, and we can look at how long it took. About 12 milliseconds. And well, this will depend very much on what platform you're on. But I can look at what this is actually doing. It's all reducing this thing, which is bfloat 16 of this shape. So I can compute 327068 times 8192 times 2. This is the number of bytes that I'm sending. And I can go look up the ICI bandwidth, which is the interconnect bandwidth, which is, again, 4.5 E10. And this says, and there's another factor of 2 that cancels out, but it doesn't really matter. The point is, this is about 11 milliseconds. And how long did it take? It took, I've zoomed in horribly here. I think it was this one. So 12.95 milliseconds. So this is also doing a pretty good job.
I see the Jacobian matrix multiplication is all inside the both reduce.
So this, I would need to stare at these a little more closely, but my sense is this is the forward pass. And then one of these is the outer product. So yeah, that's the forward pass. This is the Jacobian outer product, and then this is the all reduce of that, and then.
So all reduce is more expensive.
Yeah, because, well, I mean, this will depend on the platform you're on, and it's like one of these trade-offs that GPUs make with, how expensive, how much you want to give these like expensive NVLink and NVSwitch connections. TPUs have these fairly fast ICI connections that are sort of nearest neighbor connected. But the point is, I mean, this is one reason why people don't do pure data parallelism, is because you're just sitting here waiting for this all reduce. And what you'd rather do is some other work that you could efficiently overlap with this communication to not just block on it. And to be honest, you probably could implement an all reduce in such a way that you like kind of overlapped it with some of the computation. But we'll go look at other stuff now, like FSDP or zero sharding tends to be somewhat better in this respect. There are just like a lot of other solutions that won't be this egregious. But the lesson I want to make here is sort of like, we wrote this code where we said, OK, we're going to compute a mean here. And we told it the input sharding was just standard data parallelism. And then we computed, then we ran XLA, and it did kind of the right thing. And in fact, the performance was actually pretty reasonable. I'm not saying this is what you want to do, but like the compiler has actually done a pretty good job. And so there's this general pipeline where you kind of like look at it, you think about what you want to do, you express it pretty directly in JAX with these parallelism APIs, and then you like look at a profile and you see if it's done a good job. And so now you can do actually a lot of more sophisticated things. And I think this is where you start seeing JAX actually be sort of significantly better or more expressive than other solutions. So here I'm going to use basically the same mesh, but we're going to do FSDP. And FSDP is something where you shard the weight matrices along the same axis that you have data parallelism on. And essentially what you do is you're all gathering the weights just in time. So you're about to do a matrix multiplication. You like gather the weights in time to do that. So you are essentially saving parameter memory. And so if you're like really struggling with fitting your weights in because you have a large matrix, then this is good. And this is very similar to what we did before, except instead of the weights being replicated, we've now said like split it up along a given axis. And so we can actually look at this. We can see here the weight matrix. Here's the weight matrix, and we can see it's sharded. And you can see like different pieces of the weight matrix live on different TPUs. And you can kind of like think about what this is actually going to do. We've told it, we can even just do the forward pass for now because it's simpler. Like we've told it, OK, X is sharded along the batch axis. We can look at this, for example. X is sort of sharded along the batch axis. W1 is sharded along its like contracting dimension. We need to do something here. We're trying to multiply these things. And XLA makes some judgment call. It has some cost function for what the most expensive things to do are. And it's decided that the right thing to do is an all gather. It's decided to all gather the weights and then start doing the multiplication. And if we actually run this code, you can see was that the right one? No, that was the wrong one. We can actually print this, and you can see, here we are. Well, we can zoom in, and you'll see, for example, here are a bunch of these all gathers. And in particular, you'll see a couple of things. First of all, this is not great. Like a lot of the time is just being spent on communication here and not on anything meaningful. Although you can see, and again, this requires a little bit of familiarity with XLA, but you can see this says async collective done, which is used to mean like this all gather is happening asynchronously, and it is being overlapped with this fusion, but the fusion is not taking long enough. The matmul is not taking long enough to actually hide the time of the all gather. And why is this? Well, I think partly the answer is there are some XLA flags I need to turn on that will make it do better things. And this is like a little bit where this is frustrating. There's like a little bit of like compiler programming at a distance where you just like push it in some ways. But also, I can do some math on how long this all gather ought to take. And I can do some math on how long this fusion ought to take. And the point is, this is actually a pretty small matmul. And the weights are quite large. And so, there's some math you can do, which we could do out if anyone is interested, where, and I had done at some point here, where basically you have some kind of general rules that you can work out from just comparing the time that the matmul takes to the time that these all gathers take, where you can say, as a function of your batch size, as a function of how much compute you're actually doing, and the different parallelism strategies you're interested in, you can get away with, at very large batch sizes, you're doing a ton of compute for a fixed amount of communication. You're gathering the weights, which are fixed size, but you are computing something very large. And so you can hide pretty much all the compute, and you're generally OK. But at smaller batch sizes, you're doing imagine the limit of like 1 token. You're doing very little compute. You have to still gather these big weights. So you are still, you're going to have this exposed all gather time. And so you can I think you ultimately need to be able to reason about this to some extent to say, like, is what the compiler has come up with really bad? Do I need to go in and actually write this manually? Or is it, kind of doing the right thing given what I have told it to do? Yeah?
So by default, is this DP also sharding the optimizer states in the gradient, or is this just working on the gradient?
Well, so that's a really good question. So first of all, I think this is kind of the beauty of JAX, is that very little here is automatic, which is kind of a curse and a blessing. But if I go and look at this, first of all, the thing as I wrote it, even the training step, well, even if we look at the training step here, first of all, there is no optimizer here. I just didn't write one. Like, the optimizer state would be some running average of the first and second moments of the derivatives. And like, I didn't put it here. But if I wanted to say change this from being just sort of naive SGD to like SGD with momentum or something, I could essentially add some more parameters like DW1, DW2, which are now like running means. And I would also then, DW1 equals something, I could write something that would like average it with the new derivatives and stuff like that. And now, maybe there'd be a D embed just for consistency. And now there's a question of like, OK, well, these are now just parameters. They're now tensors that I'm passing into the program. And so I get to decide how these are sharded. And so when I go and actually call this, I would have to allocate like, DW1 and DW2 in the same way as I'm doing here. And I could shard them like along the data dimension, or I could not. And if I do shard them, then I'm doing like 0, 3, and I'm sort of doing what you would want. And if I don't, then they're replicated, and you won't see the like async optimizer all gather or reduce scatter or whatever. Like, the compiler will figure that out. And so that's pretty manual. Yeah.
One question, like, you have a large transformer with multiple layers,
Mhm.
and you shard it across the 8 TPUs. So would 3 layers go on each TPU by default, or I'm sure that you can customize it, but what's the default behavior?
Yeah, so you control that. I think this is, so I wanted to make some snide comparison to PyTorch, because like, you have like with PyTorch, for better or for worse, you have like, this. You have like some FSDP thing, and you like wrap your module in it. And maybe, essentially what this does by default is it flattens every array. It splits it up over all of your devices, and then it issues an all gather or reduce scatter like ahead of time. And this is great, but like, sometimes I don't want, like, I have small parameters like layer norm scales or things like this that I don't want to be all gathered because they shouldn't be, or I don't want my array to be flattened, or I want to mix FSDP with model parallelism. And so I can't have it just be like flattened kind of naively like this. And so you can implement all of the strategies you're describing with sharding. So if you want to do pipelining is actually the worst instantiation. It's like the one that fits the least cleanly. You can have essentially, and the way this is often done is, I would say essentially like W1 equals like num layers. So I would specify like, there's some number of layers, and it's now like, I'm now imagining there are multiple of these. And I could just do jax.device put W1 like pipeline, data, none. So now this is essentially sharded across the layer dimension. So I would create a mesh that has some TPUs dedicated to these pipeline stages and some dedicated to FSDP. And I can just go and do that here, where I can like look at my mesh and I can say, well, instead of 64.1, maybe I'll do 8.8, and I'll call this pipeline, and I'll call this data. And now I have a mesh here, 2D mesh, and like you can imagine, the layers split along one axis and like the split along the other. And then how would I do this? Well, pipelining is a little bit hard to express often, but you would essentially p-permute the weights along the pipeline dimension. So you would just, your transformer would be something like, for I in range layers, like, mat mul W1, and then like P W1 equals P permute W1. And there's in fact like a jax.lax.p permute axis name equals pipeline. And this would like, rotate them along the pipeline dimension by 1. And then I would, just kind of do the mat mul again. And so, you can kind of write this explicitly. And this,
JAX will just compile.
yeah, and JAX will just compile this. This will just work. So
Add skip connection, JAX will just compile.
yeah, anything will work. I mean, it won't work because I wrote pipeline, but it's like there are sharp edges for sure. Like, it's a little bit hard to think about like, okay, now W1 has a layer dimension, and like our activations are going to have a layer dimension, and you're going to have to think about how to permute them all. In fact, I would probably permute X and not W1. Like this would be the activations, and the weights would stay fixed. But I could just JIT compile this, and it would just work. So, is this better? I mean, it's kind of a pain sometimes. You do have to kind of understand what you're doing. It's not quite as simple as just like. But I actually don't think there's any framework where it's just really simple to do. So I think this is a reasonable solution. Another thing you could do with pipelining is you could write a single layer in a pipeline, and then you could essentially like explicitly run the pipeline code on each machine separately. It's sort of like what people would call MPMD pipelining, where you like have multiple programs running on multiple like subsets of the mesh, and you could like device put the activations from one to the other. But the point I want to make is just that these things are all kind of like expressible within the abstraction of the sharding interface. And in general, it's quite powerful. And so without deleting too much of this, like here is model parallelism. So I now have a data axis and a model axis. So again, it's now a 2D mesh. And I'm going to put the tokens, data sharded. Actually, this is left over from, this is a combination of FSDP and model parallelism here, where I'm saying, the output dimension is sharded along model, the input is sharded along data. If you just wanted to do pure model parallelism, you might do something like this, where now it's just sharded, the weights are just sharded along model. And I can actually run this. You can see what it does. Give it a second. Hopefully this is not too slow. But what we expect here is essentially it can do a somewhat efficient all gather, reduce, scatter map mul usually often with a collective map mul. And so what you can see here is this while loop. I don't know how clear this is, but what it's actually doing here, which is not maybe obvious from looking at it, but it's trying to emit a collective map mul. And this is a word we use for when it overlaps the communication and the computation of the map mul. So what it can do is it can do like a couple of rows of the map mul, and then it can take the result and like send it to the next device and start like reducing the output over that axis. And it can just sort of do this in a loop and hide the communication time. So here you can still see a lot of exposed communication time. Like this collective permute is a communication operation. And this is largely because we're not actually doing very much work. If our axes were larger, we would see less hidden. And I'm sure there's some flags I should tune. But like, you can see what it's trying to do, and you can look at the performance and sort of compare it to how good you would ideally want this to be. And in this case, I suspect because I'm missing some flags, it's not actually very good. I haven't done the math, and we could do it now in a sec. But the point is, this might actually be a moment where I would actually want to go and say, this is really bad. I'm going to go do this manually. And I don't know how many of you went to like Sharad's Palace talk this morning, but you could very easily write this in Palace, and it's actually something that's quite clean to express. There's I had looked this up earlier, but there's like a nice tutorial on this, a collective. Somewhere here is a good collective map mul implementation. I guess this is sort of more or less a collective map mul, where and I have another example that's written in pure JAX, where it basically like it does a bit of the map mul, it like does a permute, it like the actual op is like if if you want to see it. Like this is an explicit collective map model where you can see it basically like it has a for loop. Inside each loop, it like slices out a bit of the matrix. It does a bit of the map mul. It like p-permutes the result. And this is done in JAX, but you could write a similar thing in Pallas where you actually explicitly control the DMAs sent from one device to another. And this is a little bit too TPU specific, but you can do this now with Pallas and Mosaic on GPU as well, where you can kind of bypass nickel and try to actually write your own like send receive ops. And in general, I think that we have at least found, this wasn't true I think a few years ago, but that you can write pretty much anything you want, mostly in XLA, but then if it starts breaking, you used to just like have to nag the XLA compiler people until they fixed it. And sometimes there are still flags that you need to track down or things that will be helpful, but generally now you can actually just go and intervene and write what you want. One thing that's often true then is there are also ways of intervening on sharding. So this is all done, and I can maybe take a step back and describe this in more detail. The way that this all works is using XLA has a system called GSPMD, which is a automatic partitioner. And so what you do is you have a program that has some semantics, and you have sharding specified on the inputs and optionally on the outputs. That's what we've been doing. And XLA has some cost model where it says, okay, I could add a all reduce here, or I could add a reduce scatter here, or I could add something else. And each of these would have some cost, and maybe I could overlap it. And it decides what to do. And it's gotten a lot better. It's gotten to the point, it's very responsive to Gemini development in particular. So, if Gemini finds that something isn't working very well, it can, XLA people will often be on it. And if you look at the XLA code, which, increasingly is being open sourced, it's just a giant wall of pattern matching, essentially, where it's sort of thought, okay, this, works well in this setting, and this works well in this setting. And, there's a condition when to emit a collective map model, things like this. And but sometimes it doesn't work, and so you'll end up looking at a graph, and for example, here it's decided to emit a collective map model because it's decided that the intermediate sharding should be like model sharded along the output, something like that. And we can actually intervene with this in a bunch of ways. So one thing we can do is actually write manual sharding annotations. So we can, in particular, there is something called jax.lax.withSharding constraint, where we can say, like, I'm going to enforce that, in fact, this has an extra axis. I'm going to enforce that this thing here is sharded in a certain way. And this tells the XLA compiler, like, you must respect this constraint. And so if you see in a profile something really wacky where it's like doing a collective, like doing a all gather where it shouldn't be. And there are many operations where XLA kind of struggles. Like if you have a sharded matrix and you try and take a slice out of it, often XLA doesn't know whether the slice you're taking is in the same shard as you or in a different shard. And so if you try to do that slice, it will just all gather the whole array. And so to get around that, one thing you can do is you can add these annotations, or you can write device local code. And this is a new interface that JAX supports called ShardMap. That's been around for a little bit. I was sort of showing this earlier, but in particular, ShardMap lets you write device local code. And maybe I'll even do, kind of like a live demo. Like if I have, this array, let me see if I can find an example. So like, yeah, if I have this array W1, let's say, that's sharded along, how is this sharded? So yeah, this is now, well, I'll just rerun this. So yeah, W1 is now sharded along data. I can essentially write fung foo. And I can run shard map, I guess, foo. I think this will work. It might take a second. But yeah, so I'll mesh also. And what you'll see is that, so this thing had shape 8K by 16K. But in fact, when I look inside foo, what I'm seeing is I'm seeing the local view of like what it looks like on a single device. And if this were sharded along model, for example, I would see like 1024, 2048, because what I'm doing here is I am like I'm telling it to just run this code locally. And so I can even do crazy stuff like I can write jax.lax.allGather, and you'll see like the thing that came out was it has this extra axis now, which is of size 8 because that axis, that mesh axis, was of size 8. So now I can actually just explicitly say, like, I know for a fact there is no communication when this is commented out. Here I've added communication explicitly, and now this works pretty well. So generally, this is often if you want to do like, if I wanted to do a slice, like, if I wanted to take like the third axis, the third entry, like, I think this will probably work, maybe with a little modification here. Oh yeah, let's just do this. Can't be statically, I don't care. Yeah, here we go. So I just went, I mean, it doesn't really work because I didn't put any entries in it, but I just like went and took the third entry from each slice, which is like kind of actually a pretty hard operation to express without looking at the device local view. And so if you often see weird things happen, you can actually just go in and say, I'm going to write local code. And so sort of to zoom out a little.
Quick
Yeah.
question. So it should be able to figure out the out specs, right? We shouldn't have to.
Well, so in many cases, yes. The only case where it can't is, let's say that I like, well, there's first of all, there's certain operations where it's like a little hard to tell what the, let me think about this for a second. Like, I guess if I do this all gather, in theory, it could probably infer that the output should be like only sharded along model. But there are quite a few operations, like if you do sort of complicated reshapes, it's like quite hard to statically infer. Like if I flatten the array in a bunch of places, it's kind of hard for it to statically infer exactly what the sharding should be. And so we're kind of just writing naive local code that doesn't really propagate shardings. And then when I zoom back out to the local view, I need to tell it how to combine the local views into the global view. And so, for example, I might stack it along the data. Like if I had shard mapped along the data axis, I want to glue it back together. And I need to tell it essentially like which axis to glue it back together on. So like when I had the all gather example, it had it showed up with an axis of size 8, which was like the number of shards. But I could have told it to put that like at position 2 or position 3 in the array. So it's sort of, you're basically right that it doesn't need to be there, but like it sometimes is needed for like full specificity.
And it can introduce additional communication at the end.
Yes. So you can force it to reformat to this shape. So maybe to zoom out a little bit, I mean, just like give a bit of a sense of what large scale training looks like. Generally, for Gemini or for any of the LLMs we build, we try to write code that is as close as possible to just basically being pure JAX. So you just try to write the program fairly simply. The attention is, in most cases, just pure JAX. And then there are some cases with very complicated operations, like some of our ragged attention, like flash attention style things, or we have an open source kernel called Splash Attention that Sherrod and others built, which is like dynamics, like padding aware attention that can handle many different sequence lengths. These things will be written in Palace and kind of maintained separately. But there are relatively few places in the transformer where this happens. I had even pulled together a collab before where I showed like, this is kind of like a mini version of like a real transformer that we might have. So like, here are like, these are the QKV projections. You just generally, mostly just these einsums, pretty standard, softmax, QK products. In a few places, there might be, einsum. There might be a few of these with sharding constraints if it looks like JAX has done something kind of wrong and we've just needed to add this. I think this has flash attention. Maybe this is flash attention. Let me see if this does. Okay, I had one earlier that would replace the attention operation with flash attention, but fundamentally, you can essentially just write attention kind of normally, and it works pretty well. And then, then you control the sharding. So in general, it's almost trivial to go and say, okay, I'm going to run this on one GPU or one TPU, and then I'm going to scale it up to run on like 500 or 1,000 or 10,000. XLA also abstracts a lot of this away. So if you want to do something that's like, and you can run across multiple what we call pods. So TPUs are made up of these sort of like densely connected ICI domains called pods, and then you can actually do data parallelism over like the data center networking, where you can do this over like a separate axis that XLA is able to manage. So in general, I'm like, there might be a few places where we also put shard mapped code in here where you need to do some complicated operations for like a mixture of experts model that are like difficult to express. And a couple of us wrote a book which has some sort of interesting bits on this, and like there's some examples here of like some problems to work of like writing mixture of experts code where you need to do routing, and it's often much more natural to express it in like a local view rather than in a global view. So, I think there are nice libraries in JAX that help with large-scale training. The cloud folks have written this framework called MaxText that like does do a lot of this. There's also, especially for inference, a really, really nice little library in this badly named JAX LLM examples repo where they implemented Llama 3. And it's actually just really worth kind of staring at this, where you can see they sort of implement a lot of this. There's like a weights object that has, so you have a bunch of these weights, and these all have, essentially each axis gets annotated with kind of like what it is, and then you can map the shardings onto these. So like FSDP or model, I guess, sharding rules. You can specify sharding rules. I don't know where it is in here, probably here. But you can just specify like FSDP by just like annotating these with like, this is going to be the batch dimension. This is going to be over sequence. And this is more or less generally what our transformers look like. And then, you just like, we sometimes will use libraries like OptAX for optimizers, or in the past, in some cases, we've used Flax or NNX for the transformer. But ultimately, like, there's sort of a beauty to JAX, which is that you write what you want in NumPy, and it just kind of works, and it actually does scale pretty well. So in general, I think that it's kind of like good advice to follow. And XLA does a pretty good job of compiling things that you want, and you kind of do need to develop a good intuition for the roofline models of like, for your given platform, how long should this all reduce take? How long should this all gather take? And if you're really far off that, then maybe go figure out how to do something different. So I'm very happy to take questions now.
How well do Flax and OptAX work with different sharding?
Pretty well. So the nice thing about things like, well, both Flax and OptAX is that Flax is sort of like, it's like an impure framework that then you purify into these pure functions where it produces a pi tree, which is the parameters. And so once you've used Flax or OptAX to produce, OptAX produces these state objects, which carry the like optimizer state. And these are themselves just pi trees. And so what you do is you would simply generate the parameters or the optimizer state, and then device put those parameters as you want to a given sharding. So like I had sort of thrown an example in here where, this wasn't using OptAX, but like, let me zoom down eventually. It's here somewhere. Yeah, so here's like a tiny little transformer, and you allocate the weights, and the weights are annotated with like the shapes, sort of like the axis names and initializer or something. And if you had an optimizer state using Flax, Flax also allows you to attach kind of like metadata like this to the optimizers. And so you can use that to say like, this is an D model input dimension. And then you can do essentially like, essentially like jax.tree.map, where it's like, and it's like, if x is equal to like, D model, then, return, this is not how Lambda syntax works, but like return, model. And so you kind of like have some logic for mapping the various axes of your mesh sort of programmatically to shardings. And then, and it's, it's actually really fun kind of looking at, I guess I mentioned this, but for example, this was the model parallel dimension, and the XProf also includes some really nice things like you can look at how much memory it's using. And in particular, this argument size, 128 megs, if I go back to like one of the earlier versions that were not, this was one of the original ones. If I look at the memory viewer for this, Sorry, I guess that one is a bad example. Oh, that's the wrong. Okay, look at this. This was using like a gigabyte of memory per device. But then when I switched to model parallelism, where I did more sharding, it's now down to 128 megabytes because it's sharded 8 ways. So, it's in this case, like we could have then scaled up to a much larger transformer and it would have worked properly. So, I don't mean to diss other frameworks, but I think that generally there's that kind of beauty to just how explicit you can be with this. And you can rely on the fact that like this will use exactly the amount of memory that you ask. And there's sort of no spooky action at a distance. Well, at least not in the sense you don't just like wrap your module with some like FSDP thing and kind of hope for the best. Like you are pretty aware of what's going on here, and you can like control it at a pretty deep level. Yeah.
A couple times you mentioned XLA flags that are important around for performance and stuff. Is there like how do you know which ones to use?
That's a very good question. Sometimes, so I think this is an area where the XLA team is getting better, and if any of you are going to be here tomorrow, you should probably ask them. Typically, it's just like you'll find it in the code somewhere, or you'll like hear about it from someone. But I think like OpenXLA, like I'm curious if this is. Yeah. Okay. So I guess here, here is a giant proto of flags that you can tune, and like async XLA TPU enable. I'd have to find it, but generally they're just somewhere in this giant morass of flags, and I think this is an area where XLA can stand to improve. I think in general also there are some like very good resources. I do shill this little book, which like does have some good information on how sort of all of these roof lines sort of come about, and like sort of some estimates of like actually how much model parallelism can you get away with, or how much FSDP can you get away with, or like generally how does shard map work, or like there's quite a nice section on training here where you can actually essentially, so like some of the stuff from like this plot comes from this, where you actually can derive these estimates analytically from like a model of how this all works on the hardware. And it's interesting to like maybe try to map this onto GPUs as well. Like GPUs, for example, have a very different point where you switch to pipeline parallelism compared to tensor parallelism, or FSDP. So LLM training on TPUs, you can get away with a lot of FSDP because you have these very large ICI connected domains where they have like very high bandwidth between the chips, whereas GPUs tend to have these small like 8 or 64 way like NVLink like nodes that then are connected over lower bandwidth like NV switch, and so you end up doing a lot more pipelining on GPUs. But it's like kind of important to understand where this like crossover happens, and to understand that like it isn't just magic. Like someone actually did just sit down and figure out like how much bandwidth do I have and what can I get away with. And there's this kind of neat co-design also where NVIDIA or AMD or Google will sit down and say, okay, our like models are going to move this way, but also we're going to give ourselves more ICI bandwidth for the next generation. And then the next generation, you're like, okay, well now I can like do some kind of crazy new ideas because I actually have the bandwidth for it. So, both, I imagine if you look at the LLMs used by every like major AI research lab, like they're kind of customized ultimately to the hardware that they work on. And I wouldn't be very surprised if like transformers are going to change a lot. Like let's say with like Trillium, which is the new TPU, one of the new TPU chips, has a lot more flops per chip. Like even the flops HBM or flops bandwidth ratios are much higher, and so like you end up getting like much beefier models because like you just have spare flops, and so you don't want to strand those. And I think you're likely to see something similar with Broadwell, where you're going to start seeing like kind of like chunkier models because they like have extra flops to work with.
Can you talk more about your book?
Sure. I mean,
how you ended up leading this book, and why you wrote this book, and how did that happen?
Oh, I don't know. I think that especially within Google, I think there's just one of the things that's happened in the LLM space is because no one is publishing, or like none of the big labs are publishing, a lot of knowledge just doesn't get communicated in a way that I think it would otherwise, where people would write papers and tutorials and blogs and guides and stuff like that. And so I think that but that actually has consequences where even within Google, people don't kind of have a mechanism for learning how the systems work. And so I think this was an attempt to try and be like, hey guys, like this stuff actually does have rules, and like a relatively small number of people understand them. Like I learned this from one guy who learned it from someone else who has now left to start a startup. So it's kind of like there's a cool chain of like knowledge sharing in the field. And I do think both for training and for inference, I think the kind of system stuff I'm talking about today actually is like a very fertile area for research, because I just think no one is publishing. You don't actually need large compute clusters to do this work. Like it's very important, and it's a fun thing working on this, because like sometimes I can just like tune an XLA flag or like fix some bug and I get a 3% improvement in efficiency, and then I've saved Google like $10 million because the cost of these training runs is so immense. And so like if you can write a little paper or like fix something small with these kinds of tricks, or like just even understand them slightly better, there's like kind of dramatic alpha to be had there. But I don't think a lot of people do understand it. And it's just kind of like random algebra. Like here is kind of like, what is this? This is looking at tensor parallelism. So if you're doing like model or tensor parallelism, you can say like, essentially for each mapmo I'm doing, or for each layer I'm doing this many flops. And then I know how much compute I'm doing, and I know how many bytes I'm sending around. I know how long that takes. I can just figure out at what point I become bound by communication. So essentially I can go up to like essentially the feed-forward dimension over about 2,000. So if the feed-forward dimension is like 16K, which is not uncommon, then I can go up to about 6-way model parallelism. And that's like, you often see this if you go stare at some code base. Like the model parallelism might be 4 or 8 or something like that. And that number isn't magic. It just comes from like, some bandwidth estimate that you could do for GPUs as well as for TPUs. So I don't know. It's just like a bunch of random stuff, but there's also some good stuff on like transformers here, where it's like, I think probably it's actually worth understanding like exactly every tensor in a transformer. It's like it used to not be the case that there used to be a lot of architectures and like, you kind of could pick your favorite, but now it's like a lot of my daily work is like, okay, this little tensor here, is doing this many flops, and it's like causing this thing. You just can't do that kind of work unless you're like intimately familiar with all the details. So I think there's something kind of neat about actually trying to pick up this like kind of low-level knowledge. And I think there are another thing when I was thinking about making this talk, I think there are frameworks that do training, and to some extent, like maybe your best bet, especially as like an individual, is to just like go get, I don't know what the best one. I mean, Google's is max text, that the cloud is open source, to just try it. And people try this, and it does work, but past a certain point, it's just so, we're running these models so close to the edge of like the hardware that we have. We're just trying to always get like, can I get Llama, 70B to run on like my 8 GPUs, or for us, like, can I get, a trillion parameter model to run on like, 1,000, 10 million GPUs, whatever. And so like, it always ends up coming down to a systems problem. Like, it's very rare to actually be able to totally divorce things from the hardware.
What's the recommended way of reading this book? Is it better to read it front to end, like all of it doing problems, or is it the sort of should be treated, parts of it at least, should be treated as more of a reference book where you start working on some problem. Let's say you are running into some issues related to parallelism, you don't know what the best strategy would be, and you go and consult, and then you come back.
I think generally, yeah, like each part can probably be read mostly independently. There are a couple of sections, like there's a section on sort of the sharding syntax that we use that's very much similar to the JAX syntax. It's like it's kind of used throughout, and so kind of worth reading. I mean, all of this is premised on this idea of roofline computations, where you're like, how many flops am I doing, and how many can my accelerator do? And so I think it's sort of worth reading linearly, but there are also problems in each section, and you don't need to like do every one, or you can like pick a section that's interesting. Like the most relevant to this talk is this programming TPUs and JAX section, where you talk about JAX.jit and also shard map, and there's a new interface called sharding in types, where you can actually write the sharding explicitly. So like let's say I just do this for a second. So like I can, I'm doing the same thing here, but what I can actually do is I can print the sharding inside the JAX function. So instead of sharding being propagated by the compiler, it's now propagated at the JAX level. So I can now actually just like say, like, is this tensor data sharded? Or like, how many ways is this sharded? And JAX handles that. And in some cases where, for example, like here I'm trying to do a map mul of two things that are like both sharded along the same axis, but not in a way that's like very compatible. And it complains because it says like, oh, dot general with these inputs is illegally sharded. And so now it's up to me to decide, like, how do I want to resolve this? Do I want to all gather this? Do I want to all gather this? Do I want to like do an all to all here? I kind of have that choice. And so I can actually go and write like out shardings equals p of data none, for example. And sorry, this is out sharding. Keep doing that. And like this now passes because I've now sort of resolved the ambiguity in how to propagate the sharding here. So this is also kind of cool where, the XLA sharding annotation function just has to do its best because it can't actually ask you like, what do you want here? But if you do sharding in types, which is kind of a new feature that more and more of Google's code bases is moving to, it can ask you, it can complain and say, I don't know what you want here, and then you have to go resolve it. Yeah.
So this is bypass GSP?
More or less. So essentially, this will lower to those with sharding constraints that I was talking about. It will essentially like annotate pretty much every piece of the graph with a sharding constraint. So GSPMD is still kind of invoked, but it almost does no work because like this will infer and kind of impose the sharding at the JAX level on every part of the model. And so you can even do stuff here. Like I can say, if like, the output dot like dot spec of 0 is equal to data, like, do like return my, fancy all gather kernel or something. I can't spell. It's just something like where I can now actually even have my code kind of like dispatch different commands based on sharding in a way that like wasn't possible before. So yeah, this is like an alternative to GSPMD that, still has some sharp edges, but is often less surprising than GSPMD.
But this would still rely on GSPMD to introduce these.
Yes, so it will. So it's more like you hope that GSPMD, if like the tensor before says it's it's sharded along this extension, and immediately after it's not sharded, it sort of assumes that XLA will add a reasonable communication primitive there. But it's not the same as shard map, which is sort of like an alternative to this is to write this all in a device local view and just write the all gathers and the reduce scatters like manually. So there's always this. This is the kind of the beauty and the curse of JAX is that you do have the ability to like intervene at any of these levels, and it's kind of a moving target of like what is the simplest to write, what is the most performant, what leaves your code in the best state.
What's the best way to express pipeline parallelism?
Good question. Yeah, there's some joke a friend of mine said, which is like no code base survives implementing pipeline parallelism because like it doesn't fit the same abstraction. You can't just be like shard over the pipeline axis and then everything works. Like you need to have some kind of a role or like a permute operation. Google has tried many different versions, and I think Google does this less than other companies. The kind of two models are like, one is like this, the thing I was describing before, where you have an extra layered like pipeline axis of the weights, you roll over it, and everything is done in the JAX land. The issue is, as you probably know, is that there are all of these crazy like bubble-free pipeline schedules where you have to like very precisely overlap the commute and the communication and like the gradient updates at a particular step. And you can implement this in this way where you have kind of like a schedule where you're like roll and then apply the gradient and then roll, and you can kind of control it at that level. But you can also, and I was just calling this MPMD pipeline, you can kind of like compile like 3 different functions, which is like the gradient up, like the optimizer update, the forward pass, and the backwards pass, like the sort of 3 things that you do in a pipeline, like these bubble-free schedules. And then you could write like Python or C++ code that like actually executes the bubble-free schedule by calling multiple JITted functions. And then you can actually like you can use device put outside of a JIT context to say like, I'm going to now send this activations to the next thing, or I'm going to send the gradients back to the previous thing. So in my view, that might be the most the least horrible, because like writing a full bubble-free pipeline schedule in JAX sounds miserable.
How much gain is that actually? Is it worth it? That for extra complexity for going all the way in pipelining when you can just buy a few extra TPUs?
Each model looks different, and sometimes you need pipeline parallelism because your model doesn't work with other schemes. Generally, TPUs are very forgiving when it comes to using FSDP and model parallelism. So you can, because you have such a large pod of like highly connected GPUs, like I didn't show this because I assume people sort of are familiar with it, but like, you have these like crazy super pods of like, like thousands and thousands of these GPUs connected to each other. So, in general, you don't need to do pipelining during training as much, but you can, for example, there's reasons to do pipelining during inference, which is you can get faster, and you can speed up inference by doing pipelining in a way that you can't with, because like during inference, you can't really do FSDP because you don't have a big batch. So all you can do is model parallelism, which as we've seen has like a pretty discrete cutoff where it just stops working. And so past that point, the only thing you can do is pipelining. But the good thing is at inference, you don't need to do a fancy bubble-free schedule because you don't have gradients. So pipelining at inference time is a lot easier than pipelining during training. So TBD whether, I sort of don't think it's worth doing on TPUs, but there might be a reason to. Cool. Well, thank you all for coming. I hope you enjoy the rest of the day.